Hello, we continue the series Verge3D for Maya Basics. In this part of the tutorial, we'll discuss possible ways to optimize our application. There are numerous factors affecting the performance of a real-time 3D application. For online 3D content, the most important factors are the number and size of textures, the number of shaders, the number of so-called rendered calls, and the overall file size of the assets that are loaded over network. To get an idea of your application structure and possible ways for optimization, we can go to the puzzles editor and add the puzzle called Print Performance Info. Then, if we open the browser console with F12, we can see some information about our scene printed there. Here we can find how many render calls are used to render our scene, how many triangles are contained in the geometry, and how many shaders are used. Then goes the list of materials. Some of them were created in Maya, while others are generated by the engine for internal use. Finally, we can find the list of all textures used in the scene, including their names and size. So, in order to make our application load and work faster, and also reduce the memory footprint, we should first try to reduce the number and file size of textures. Let's open up the application folder, where all the textures are stored. If we look closer at the textures, we can notice that many of them are merely black and white images. This means that we can pack these images to the RGB channels of a single texture. Also, the textures are in PNG format, and since we don't use transparency, we can safely convert them to JPEG format to reduce the file size. The only textures we spare converting to JPEG are normal maps that are very sensitive to lossy compression. So we are going to leave the normal maps as is. For manipulating images, we'll be using GIMP, but you can use any other graphics editor to do the same. So we'll start by dragging our black and white images from the application folder to GIMP and packing them to the RGB channels of a single texture. To begin with, let's do it with the metalness texture for the carbon material, and then add the roughness texture as the second layer. To combine these images, we can go to the Color menu, then to Components, and select Compose. If this option is not active, then you first have to go Image, Mode, and switch it to Grayscale. Okay, let's select Compose. In this window, we can assign our layers to whatever channels of a future texture. There are no strict rules on what channels we should use, but we'll be following the recommendation of a GLTF standard, according to which the red channel is reserved for the occlusion map, the green channel is for roughness, and the blue channel is for metalness. So we won't be using the red channel, since we have a separate ambient occlusion map baked for all parts of the model. Let's make it pure black. To the green channel, we'll pack the roughness texture. And to the blue channel, we'll add the metalness texture. Click OK. Now we obtained a single texture. So let's save it. In GIMP, this operation is performed via File Export menu. Let's use the following naming convention. First goes the name of the material, carbon, then goes the type of a texture, Occlusion-Roughness-Metallic. Finally, we'll be using JPG format for our image to make it smaller. We'll set the compression quality at 93 to balance between the file size and quality. Although there is not much, if any, improvement in file size, having a single texture instead of two is much better, as it saves video memory, which is very important for mobile devices where memory is scarce. Okay, let's proceed with the other textures and convert the base color texture of a carbon material to JPG format. Also set the compression to 93. As a result, we reduced the file size from 800 KB to just 300, which is a significant improvement. We can delete all images as we no longer need them. Let's also check the normal map. Although we are not going to convert it to JPG, it is important to ensure that there is no unused alpha channel in it, since it adds up to file size. In our case, there is no alpha channel, but if your image has it, you should definitely remove it from an image to make it smaller. So this is it with the textures of a carbon material. Let's proceed with plastic. Save the base color texture as JPEG using the same naming convention. In the beginning goes the name of the material, then the type of the texture. Now let's pack the roughness and metalness textures similarly to what we were doing with the carbon material. Let's proceed with the wood textures. Speaking of wood, we have only roughness texture in this case, as there is no metalness at all. And it seems there is no need to pack anything. However, we'll create this texture anyway in order to obtain a consistent structure for all three materials. We'll need this to be able to use just one shader for all three materials later. So let's provide pure black colors for both red and blue channels. This means that the metalness value for the entire surface will be 0. As a result, all the textures for occlusion-roughness-metalness have the same composition and can safely be replaced with each other in the same shader. So we are done with the textures and now we are ready to handle the materials. Get back to Maya. As we can see, the textures are missing since we converted them and changed their names. This is okay, since we're going to refactor our shaders anyway. What we want to achieve in the configurator is that it works not by replacing materials, but rather replacing images in the same material. As such, we no longer need the swatches and can delete them. We no longer need the materials themselves, so launch Hypershade and remove the materials for wood and carbon. So let's restructure our shader so that it can represent all three materials using different sets of textures. First of all, let's delete all the old textures. Delete the base color texture, which we converted to JPEG. Also delete the metalness map, which we packed to a single texture. And the normal map, which we simply renamed. And finally the roughness texture, leaving only ambient occlusion texture, which we didn't touch. Open up the application folder and drag the new textures to Hypershade. First of all, let's add the plastic's base color texture, which we simply reconnect to the material. Then goes the normal map, which we also connect as before. However, we must remember to switch its color space to raw. Finally, we add that single texture in the channels of which we packed the roughness and metalness information. Now we need to retrieve this information from the channels. Remember that the red channel is empty. It is intended for occlusion, but we have a dedicated texture for that. The green channel contains roughness, so let's connect it with the specular roughness input. Finally, the blue channel contains metalness and should be connected with the float composite node, just like it was before. Also be sure to switch to the color space for this texture to raw. So this is it with the shader. In Maya viewport, it now looks as before. Let's export the scene to update the application. Let's check it out by running the app. So the plastic material works as before. However, the configurator is predictably broken since we deleted the other two materials. So let's rework our puzzles to use the single shaders for all three material options. Run the puzzles editor and find the group of blocks responsible for the configurator. At first, let's delete all assigned material puzzles. Instead, we'll be using another puzzle called Replace Texture. So the configurator now will be swapping textures inside the same material rather than swapping materials. So let's add a material selector and select plastic. This is how our universal shader is named in Maya. The first texture that we are going to replace is base color. To make no mistake, let's open up the application folder from which we'll be copying the exact file names. So let's find the base color texture of carbon. Using the right-click menu, select Rename and copy the name of the image. Paste it to the puzzle. Be sure to add the right extension, JPG. Now we can insert this puzzle into its permanent position. Next texture we'll handle is the normal map. Let's copy and paste this puzzle. Paste the file name for the normal map. In this case, this is a PNG file. Be sure to switch the texture slot to plastic normal. Finally, let's duplicate these puzzles once again and switch it to Occlusion-Roughness-Metallic. Let's copy the file name. This is a JPEG image. It appears that we can simplify our setup a bit. The thing is that the Replace Texture puzzle has a slot Once Ready Do, which we can enable using the blue gear icon. So we can know exactly when a texture is loaded and can get rid of a timeout entirely. Let's move this variable setter here and delete the timeout puzzle. We used the puzzle for the normal map texture because its file size is the biggest among the images and is likely to be loaded last. Let's save the puzzles and check out our app. So initially we see the textures for plastic. If we click on the carbon button, new textures are loaded and applied to the shader. Okay, let's deal with the rest of the configuration options. Since we named the images consistently, we can simply duplicate this puzzle and type wood instead of carbon. Let's do this for all three textures. Replacing packed textures will also work flawlessly. Since we packet the roughness and metalness information into the green and blue channels of each texture consistently. Let's save the puzzles and check out the app. Both carbon and wood buttons work great. Now let's deal with the final option so that the user could return to the plastic material. Let's copy this puzzle again. Modify the path for plastic. Do the same with the rest of the textures. Okay, let's test it out. This may seem like the same result as before the optimization, but actually now the app loads and uses only the set of textures needed for the initial material, rather than all the textures used in the app. Okay, now let's optimize the geometry to reduce the number of render calls. The thing is that each separate mesh requires certain processing before sending to the video card for rendering. So, if you have multiple meshes that share the same material, it makes sense to join them into one. Of course, this is only applicable to meshes that are not animated or somehow used in the scenario as separate objects. So you can safely join such meshes and improve the rendering performance as a result. Okay, let's find such meshes in our Maya scene and merge them together. Go to Perspective mode. For the start, let's join these two covers into one object. Select them both, go to Mesh in the Pie menu and select Combine. They are joined now, however, two new objects were created in the editing history. So let's clean up the history to remove this object from the scene. Now we can rename the new object to simply Cover. Or better, covers. Next meshes we'll want to join are these aluminum parts. Select them all and combine. Rename the resulting object for more clearness and clean the history. Then we have chrome-plated meshes, some of which are animated and some are static. Obviously we want to keep the animated parts, so let's hide them for now. Now select the static meshes and combine them. Finally, we have these brass rods, which we also combine. Apparently we forgot to assign the material to this part. Let's fix this quickly in the Hypershade. So we join these meshes as well. Let's unhide everything. Restore the camera view and export to Verge3D. Let's open the browser console again. So we had 21 render calls. Let's refresh. Now we have just 18 render calls. The difference seems to be small. However, if you have hundreds or thousands of objects, the difference in performance may be stark. We also reduced the number of textures. Moreover, only a few textures are now loaded on startup, which is very important for cases when you have lots of configurable options. We also reduced the number of shaders. And as such, our application spends less time on shader processing, as a result starts faster. So let's make the last but not least optimization of this tutorial. Namely, we compress the GLTF scene so that it loads faster. This method is especially effective if you have a lot of geometry in your scene. To enable exporting compressed GLTF files, in Maya go to Verge3D menu and then open up the export settings. Here, check the Enable LZMA compression checkbox. Now we should export the scene again so that it creates the compressed version of the GLTF files. As soon as we have the compressed assets, we should enable using them in our application. To do this, go to the Puzzles editor and switch to the Init tab. Here, drag out the puzzle called Configure Application. Then enable the checkbox Compressed Assets. As a result, the application will load the compressed version of the GLTF files from now on. This particular scene is not so big to speed up the loading time significantly as a result of compression, but if you have lots of high poly models, it can really help. This is it with optimization. Thanks for watching and see you in the next video.